It's 2 a.m. The forest is pitch black. No moon, no stars, just darkness so complete you couldn't see your hand in front of your face. A moth is flying. It doesn't know it's being hunted. 30 feet away, a bat launches from a branch. It can't see the moth. But in its mind, a map is already forming, a three-dimensional picture of everything around it, built entirely out of sound. The bat opens its mouth. A burst of ultrasonic pulses fires at 200 times per second. Frequencies far above the ceiling of human hearing. Those pulses race through the darkness, hit the moth's wings, and bounce back. In less than a millisecond, the bat knows exactly where that moth is. Not roughly. Exactly. The distance, the direction, the speed, even the texture of the moth's wings beating against the air. The bat adjusts its flight path. It swoops. The moth never had a chance. You've probably heard that bats use echolocation. But do you actually know what that means? Not the word, the mechanism, the biological engineering that makes it work. Because when you understand what's really happening inside a bat's skull at 2 a.m., impressive stops being the right word. This is not instinct that scientists can't explain. And it's not luck. What bats do every night is execute a feat of biological precision that the best human sonar systems still can't fully replicate. Military submarines use sonar. Hospitals use ultrasound. We've had this technology for decades. And yet, a creature with a brain the size of a grape does it better, faster, in real time, while flying at 60 miles per hour through a forest. So here's the question driving everything today. How does that actually work? Not bats send sounds and listen for echoes. You already know that. We're going layer by layer, from the first pulse leaving a bat's mouth to the moment its brain makes a split-second hunting decision. The physics, the anatomy, the neuroscience, all of it. By the end, you'll never hear the word echolocation the same way again. Here's what most people get wrong about bats. You probably picture them as primitive creatures fumbling through the dark with a crude biological trick. That assumption is wrong. Bats are not primitive. There are over 1,400 known species, the second largest order of mammals on Earth. They've been refining echolocation for roughly 50 million years. And a 2011 study published in Nature by researchers at Boston University found that echolocation evolved independently at least twice in bats through convergent evolution. Different lineages, separated by millions of years, arrived at the same solution. That's how valuable this ability is. The variety is staggering. Some bats emit calls through elaborate nose structures to shape sound like a satellite dish. Others detect the ripple a fish makes on a water surface from 30 feet up in the dark. Yes, bats that fish, in complete darkness. Here's a number worth holding on to. The human ear detects sounds between 20 Hz and 20,000 Hz. Bats operate between 20,000 Hz and 200,000 Hz, up to 10 times beyond our ceiling. At full hunting intensity, a bat's call registers between 60 and 140 decibels. That's a rock concert, coming out of an animal that weighs less than a slice of bread, and it doesn't deafen itself. We'll get to that. Echolocation isn't one trick. It's a layered system, and each layer is more surprising than the last. The pulses a bat produces are not random noise. They are precision engineered for the hunting situation. When cruising and searching, a bat produces long sweeping calls, 20 to 30 milliseconds, where frequency slides downward within a single pulse. That sliding frequency gives the brain far more information than a flat tone. But when the bat closes within 3 feet of a target, the calls shrink to 0.3 milliseconds and accelerate to 200 pulses per second. Researchers call this the terminal buzz, a rapid-fire update stream in the final approach. Now, here's the problem. The outgoing call is 140 decibels. The returning echo can be 100,000 times quieter. How do you hear a whisper while you're screaming? A tiny muscle in the bat's middle ear, the stapedius muscle, contracts 6 to 8 milliseconds before the bat vocalizes, physically dampening its own hearing for the exact duration of the outgoing call. Then it releases instantly, so the ears are fully open for the returning echo. 6 to 8 milliseconds of advance warning. The muscle fires before the sound leaves the mouth. You blink in roughly 150 milliseconds. The bat is deafening and resensitizing its own ears more than 20 times in that same window, so the pulse bounces back. What does the bat actually extract from it? First, distance. Sound travels at 1,125 feet per second. The bat measures the time delay between pulse and echo with a precision of 1 microsecond, 1/1,000,000th of a second. That gives a spatial resolution of 0.5 millimeters, half a millimeter, in complete darkness, against a moving target. Second, direction. The bat's ears are asymmetrical, with complex ridges that distort incoming sound in predictable ways depending on direction. The brain learns these distortion patterns and calculates full three-dimensional positioning, not just left and right, but up and down, from two ears. Third, speed. You know the Doppler effect, why an ambulance siren sounds higher as it approaches and lower as it recedes. Bats exploit this deliberately. A higher frequency echo means the target is approaching. Lower means it's moving away. Some species actively adjust their outgoing call frequency to compensate for their own flight speed so that echoes from stationary objects return at a fixed reference frequency. Making moving targets stand out by contrast. They are doing real-time Doppler compensation in their heads while flying. Fourth, texture. A moth's wing covered in tiny scales returns a different echo than a smooth surface. A flapping wing creates a rhythmic flutter in the echo. The bat doesn't just know something is there. It knows something with wings is there. It can distinguish a moth from a falling leaf based on echo texture alone. By the time all of this assembles, the bat doesn't have a rough ping on a screen. It has a continuously updating three-dimensional model of everything within 50 feet, distances, shapes, speeds, surface textures refreshed up to 200 times per second. All of that from sound. The processing window between echo arriving and muscle command firing runs under 10 milliseconds in well-studied species. Your fastest deliberate reaction time, pressing a button when you see a flash, is around 200 milliseconds. The bat's hunting system runs 20 times faster than your quickest conscious response. A 2013 study from Johns Hopkins University found that bats hunting in groups face a serious interference problem. Multiple bats firing pulses in the same space. The solution: each bat has a unique acoustic fingerprint, varying call frequencies and timing so it can distinguish its own echoes from the noise. When two bats get too close, they actively shift frequencies to avoid overlap. Researchers call this jamming avoidance, like two radio stations adjusting channels so they don't broadcast on top of each other. Inside the bat's brain, a structure called the inferior colliculus contains neurons tuned to specific time delays, specific distances. Other neurons respond only to specific Doppler shifts, specific speeds. The bat's auditory brain is essentially a hard-wired lookup table. Different neurons fire for different combinations of distance, direction, and speed, feeding directly into motor commands that adjust wing angle and flight path. The whole system runs on a brain weighing between 1 and 3 grams, lighter than a paperclip. No system is perfect. Here's what bats cannot do. Echolocation works best within 30 to 50 feet. Beyond that, echoes become too faint. Bats cannot survey large open spaces the way a hawk spots a mouse from 300 feet using vision. Long-range hunting is not what this system is built for. Resolution also degrades on very small targets. Below roughly 0.3 millimeters, the system struggles. Experiments have shown bats flying into thin wires strung across their path, not because the sonar failed, but because the wire fell below the detection threshold. In very cluttered environments, the system gets overloaded. Bat species evolved for open-air hunting perform worse in dense forest and vice versa. The sonar is optimized for a specific ecological niche, not universally perfect. And moths fight back. Some moth species evolved ears tuned specifically to bat echolocation frequencies. When a moth detects an incoming bat signal, it dives, spirals, or drops into freefall. Some moths produce ultrasonic clicks that appear to jam bat sonar or signal that the moth is toxic. This evolutionary arms race has been running for tens of millions of years. Neither side has won. The bat's sonar is not a cheat code. It's one side of an ongoing biological negotiation. Remember that moth, flying through total darkness, with no idea what was coming. The bat saw everything, not with eyes, with sound. A system so layered and precise that it turns darkness into a private acoustic world only the bat can read. A 3-gram brain running real-time 3-dimensional sonar, compensating for Doppler shifts, managing interference from neighboring bats, reading the wingbeat signature of a moth, all simultaneously, in under 10 milliseconds. The bat doesn't think about any of this. It just hunts. And somewhere right now, in a forest you'll never visit, one is doing exactly that. If this changed how you think about the animal world, share it with someone today. And if you want more deep dives like this one, subscribing is the fastest way to catch what's coming next.